We use it every single second of our lives, pretty much without even thinking about it. But what is this invisible force that powers, well, everything? Today, we're going to pull back the curtain and unlock the secrets of electricity. How does it really work? Let's dive in.
Yeah, it really all boils down to this one big question. I mean, you flip a switch and boom, the lights come on. It feels instant. But what's actually happening inside those wires? What's moving? Well, to get our heads around it, we're going to start with an analogy that's actually surprisingly simple.
All right, so here's the best way to think about this. Just picture electricity as water flowing through a pipe. Seriously, that one simple idea, it's the key that unlocks pretty much everything else we're about to talk about. Okay, so if electricity is the water, then what we call current is just the flow. It's how much of that electric charge is moving past a point at any given moment. Just like a river, sometimes it's a gentle little trickle, and other times it's a powerful rushing torrent. But wait a second, what's making that water or current flow to begin with? It doesn't just move on its own, right? That's where voltage comes into play. If current is the amount of water, think of voltage as the pressure pushing it. And when we connect these batteries, these cells in a series like you see here, what we're really doing is stacking up that pressure. We're creating a stronger push to get more current flowing. Right, so this flow needs somewhere to go and needs a complete path, like a full round trip. And that path is what we call an electric circuit. The key thing to remember is it has to be a closed loop. It starts at the power source, goes through whatever it's powering, like a light bulb, and then it has to travel all the way back. If that loop is broken at any point, yeah, nothing happens. It's an all or nothing deal. Okay, so we've got the flow and we've got the path, but the really cool part is our ability to control it all. So how do we actually turn it on and off, or even dial it up and down? Well, the most basic control of all is just on and off, and that's all about whether the circuit is open or closed. Take a look here. On the left, that's an open circuit. See that gap? The path is broken, so the current is completely blocked. But on the right, it's a closed circuit. The path is complete, and the electricity can just flow freely. And here's a perfect way to think about it. A simple light switch is basically a tiny drawbridge for electricity. When you flip that switch off, you're literally raising the bridge, creating that gap we just saw. That's your open circuit. And when you flip it on, you're lowering the bridge, closing the circuit, and letting all that current rush right across. But hold on, control isn't always just a simple on or off, is it? Sometimes we need to adjust the amount of current that's flowing. Maybe we don't want a torrent, just a trickle. So how do we pump the brakes on this thing? The answer is a little thing called resistance. And pretty much every material has some of it. Materials like copper, they're like a super smooth highway. Electricity flows super easily with very little resistance. But other materials, they fight back. They oppose that flow. And that opposition is what we call resistance. It's basically electrical friction, the bumpy road that slows everything down. And this brings us to a really, really important rule. If you keep the voltage, that's the push, remember, exactly the same, then a path with low resistance is going to let a ton of current flow through. But a path with high resistance, it's going to choke that flow down to just a tiny trickle. It really is that simple. Check this out. This is a perfect example of what we're talking about. Normally, you'd use a copper wire, which has super low resistance, and the bulb shines nice and bright. But look what happens if you swap that wire out for the graphite inside a pencil lead. Graphite has much higher resistance, so even though the voltage, the push, is the same, that higher resistance just throttles the current, and the bulb only glows dimly. You can see the effect right there. Now, all of that electrical friction we've been calling resistance, it has a really important side effect. It generates heat. And that heat, well, it can be an amazing tool, or it can be a really serious danger. So how much heat are we talking about? It really comes down to two big things: how much current is flowing and how much resistance there is. The more current, the more heat. The higher the resistance, the more heat. We actually use this on purpose in things like our toasters or electric heaters. But it's also the reason why an overloaded wire with way too much current running through it can get hot enough to start a fire. The old school incandescent light bulb is the perfect example of putting this heat to work for us. That tiny little wire you see going inside, the filament, it's made of a special material with crazy high resistance. So when we force current through it, it fights back so hard that it gets incredibly hot. So hot, in fact, that it literally glows. And that glow is the light we see.
But this heating effect is also exactly what makes electricity so dangerous. A short circuit, you've heard the term. It happens when the current suddenly finds an accidental, super easy path back home, a path with basically zero resistance. And what was our rule? Low resistance means a massive, uncontrolled surge of current. And that surge creates a dangerous amount of heat, almost instantly.
So, how do we stop our houses from burning down? Well, with this clever little gadget called a fuse. You can think of a fuse as a purpose-built weak link in the chain. It's just a special, thin little wire that's designed to do one thing: melt. If the current ever surges to a dangerous level, that wire melts, breaks the circuit, and stops the flow. It's a tiny little hero that sacrifices itself to prevent a disaster.
Okay, so we've covered flow, control, and heat, but electricity has one more incredible secret up its sleeve: a hidden force, an invisible connection that honestly changed the world forever. This is the big one, the key discovery that changed everything. For hundreds of years, people thought electricity and magnetism were two totally separate things. But then, someone discovered that when you run an electric current through a wire, it creates an invisible magnetic field around it. Just like you see in this experiment, that current is powerful enough to actually move a compass needle. This was huge. Electricity creates magnetism. And of course, we immediately figured out how to make this effect even stronger. A single straight wire, it creates a pretty weak magnetic field. But if you take that same wire and wind it up into a tight coil, all the little magnetic fields from each loop add together. And that creates a way stronger and more useful magnetic force. And this idea, the ability to create a magnet that you can control just by flipping a switch, it's the foundation for so much of our modern world. This device is called an electromagnet, and that's what we're going to break down next. So what is an electromagnet? Well, at its core, it's really simple. It's just a coil of wire, usually wrapped around a piece of iron to make the force stronger. But here's the magic trick. It is a magnet that you can turn on and off. The magnetic power is only there when the electricity is flowing. Cut the power, and the magnet disappears.
All right, it's time to put it all together. Let's see how every single one of these ideas, the current, the circuits, the resistance, the electromagnets, how they all come together in one brilliant, everyday device, the electric bell.
Okay, so let's walk through this step by step. But remember, this all happens in a split second. Ready? First, you push the button. That closes the circuit. Instantly, current flows, the electromagnet turns on, and yanks that little metal hammer forward. The hammer smacks the gong. Ding! But, and this is the genius part, the very same movement that strikes the bell also breaks the circuit. So the electromagnet turns off. A little spring pulls the hammer back to where it started, which closes the circuit again. And the whole thing starts over, again and again and again, super fast. That's what makes the ringing sound. It's just an absolutely brilliant piece of design. So there you have it. We went from thinking about electricity as simple water in a pipe all the way to this incredible, invisible force of magnetism. It just goes to show you that electricity and magnetism, they're not separate things at all. They're two sides of the very same coin. And that just makes you wonder, right? What other deep, hidden connections are out there, just waiting for us to find them, connections that could power our future?